we're on the air. So, first off, I want to thank the organizers for inviting me to speak. Even though I'm not directly a geometric group theorist. And also, I should mention that this is based on joint work with the Soreen program. It's based at UCLA. Alright, so this talk is going to be about a certain type of group actions, namely actions of countable discrete groups on probability spaces. And these will be measure-preserving actions. So that's those are just group homomorphisms from countable discrete groups into the automorphism group of some probability space. Where two automorphisms are identified if they're equal almost everywhere. It's really an equivalence class of automorphisms. And when we're dealing with these sorts of actions, we usually assume, impose some natural assumptions. One of them is freeness, which is a strong sort of faithfulness assumption on the action, which says that every one of the automorphisms, except for the identity automorphism coming from the neutral element, only agrees with the identity automorphism on a set of measure 0. Then we have ergodicity, which is a sort of irreducibility assumption, which says that if a set is fixed by every group element, or is preserved by every group element, then it either has measure 0 or 1, the null or co-null. So I wanted to give one example, please. So there's one type of action that you can consider for any infinite countable discrete group, which is the Bernoulli action. So you start with your group and you fix some base probability space that you assume is not just a point. And you form an infinite product indexed by group elements. And then you let the group act by shifting the coordinates. And under very mild assumptions, this action is free and ergodic. So this is nice because you can consider this for any group. Stop me if there are any questions or comments. Okay. So I work with von Neumann algebras. So let's right away try to translate these actions into actions on von Neumann algebras. So just to remind you, the von Neumann algebra is a subalgebra of this thing here is a set of bounded linear operators on some Hilbert space. And it's a subalgebra of that, which contains the identity operator, which is closed under taking adjoints of operators, and which is closed under in the pointwise norm, under pointwise norm convergence, where the norm there refers to the norm on the Hilbert space. That's usually called the strong operator topology. Functional analysts. And a state on such a von Neumann algebra is a linear functional that sends 1 to 1 and is positive in this sense. And a state can be faithful, meaning this condition satisfied, or normal, which is a natural form of continuity. The most basic example is the example of L infinity acting on L2 by pointwise multiplication of functions. That turns out to be a von Neumann algebra. And there's a natural faithful normal state on it, which is just integration with respect to the probability measure. And in fact, this example is universal for abelian. Abelian meaning commutative. Abelian von Neumann algebras. With this language, we can talk about state-preserving actions of countable discrete groups on abelian von Neumann algebras. Now these are just group homomorphisms from our countable discrete group into the automorphism group of the von von Neumann algebra, which is just the group of star automorphisms of A that preserve the state in this sense. The point is that there's a one-to-one correspondence between actions on standard probability spaces and state-preserving actions on separable abelian von Neumann algebras. Here, standard means, there's an abstract definition, but you can think of it as meaning that the probability spaces, the unit interval, the Lebesgue measure, with perhaps some countable set of atoms thrown in. So these are, and separability here doesn't refer to the operator norm on B of H, but it refers to the strong operator topology on the von Neumann algebra. It's easy to pass in one direction. If you have an action on a probability space, and for every group element you have an automorphism, and you can take an L infinity function, precompose it with such an automorphism to get a new L infinity function. So in that way, an action on a probability space gives rise to an action on L infinity of a probability space. And if the original action preserves the measure, then the new action preserves the interval. How you pass from one to the other. Okay, so this is just slight change of perspective at this point. So of course, in this von Neumann algebra framework, you can still formulate ergodicity and freeness of actions. Ergodicity just means that if an element of your von Neumann algebra is fixed by every group element, then it has to be a scalar. Remember, there's this identity operator, which is always in our von Neumann algebra. So this being a scalar just means you're a scalar multiple of that. So that's how you formulate ergodicity. And freeness is formulated by saying that a certain projection that you can associate to any automorphism, and which is supposed to represent, it's the biggest set where the automorphism is the identity. That's supposed to be zero whenever you have a non-neutral group element. So more precisely, the projection is defined like this. The largest projection on which, if you restrict your automorphism, then you get to it. That's only that makes sense.
What does max here mean?
It just means that there is a largest projection with this property. I'm taking that one. You could also take it to be the supremum. In a von Neumann algebra, there's a natural notion of supremum over a set of projections. I'm saying max just to point out that there is a largest projection with this property. That's the one we're thinking. Does that answer your question? Yeah. Any other questions about the basic framework here? So, in my title, find the word conjugacy. Let's start by defining that. So basically, two actions, let's say of the same group, are conjugate if they're the same up to relabeling the von Neumann algebra, or relabeling the probability space. Thinking of it that way. Right. So precisely, that's the precise definition. And yeah, the notion that I want to talk about in this talk, which was one of the notions that Sorin and I introduced in our paper, is that of approximate conjugacy, where we're requiring that this identity here hold asymptotically. So to formulate that, we need a notion of distance between automorphisms. So that's defined like this. So it's sort of a uniform distance. If you look at the unit ball of A, these are now all the operators of operator norm with most 1. And you look at the difference between the values under the automorphisms, and then you take the 2 norm. Where the 2 norm is this gadget here, which when A is L infinity, this is just the 2 norm, the usual 2 norm, coming from the probability measure. And, this can be formulated purely in metric theoretical language, but I won't do that. So, with this distance in hand, we can define approximate conjugacy by saying that there exists, requiring that there exists now a sequence of isomorphisms between the Neumann algebras that asymptotically conjugates one action into the other one. And I should mention that Allegros-Kekkeris introduced an even weaker notion of conjugacy, called weak conjugacy, which is even weaker than this one. But, I won't have anything to say about that.
I know you already said you were going to do this, but is there a way to interpret that on the dynamical systems side?
Yes, so you look at all sets, all measurable sets, and then you can apply both automorphisms to that set. And then you look at the symmetrical difference between those two images, and you take a measure of that. The supremum over all those numbers. It's another way of formulating this. So that's the definition of studying. So one of the first questions that arises is, how does this compare to the standard conjugacy? And it turns out that for a lot of groups, they're very much distinct, as you would imagine. So the first thing to notice is that for this follows from a result of Popa, earlier work of Popa from 2014, which is in turn based on the Ornstein-Weiss theorem, 1980, that all free ergodic actions of a fixed infinite amenable group are automatically approximately conjugate to each other. If you know what orbit equivalence is, this is reminiscent to the Ornstein-Weiss theorem. It says that all free ergodic actions of amenable groups are orbit equivalent to each other. But there isn't a clear-cut connection between orbit equivalence and approximate conjugacy in general. So that's the first thing to notice. And then, so this shows in particular that for infinite amenable groups, there are lots of actions that are non-conjugate, but that are still approximately conjugate to each other. We were able to extend that a bit. We have this proposition that if we have a group with an infinite amenable quotient group, so say the free group on two generators, then gamma emits uncountably many free ergodic measure-preserving actions, state-preserving actions, in my terminology, that are mutually non-conjugate, but that are all approximately conjugate to each other. And just one remark about the proof of that is that it uses the well-known fact that two classical Bernoulli actions of an amenable group are conjugate if and only if they have the same, if and only if their base spaces have the same entropy. A classical invariant, which I also won't say anything about. So these are groups that have an infinite amenable quotient, and at the opposite end of the spectrum we have groups with property T, where then the situation is the opposite. Assume that gamma has property T, and if you have two measure-preserving ergodic actions of that group that are approximately conjugate, then they're already conjugate. And I want to talk about the proof of this result. It will require me to talk a bit about some objects in von Neumann algebra theory. I hope you'll bear with me. Right. So first, what's the definition of Kazhdan's property T that we'll be using? So not too hard to see that, yeah.
Okay, so another question, sorry. So your definition of conjugacy, does that correspond to the conjugacy of the measure preserved of the dynamical system's definition of conjugacy?
Yes. I mean, it's just after relabeling the space.
And what does your definition of approximate conjugacy correspond to? Is it something dynamical systems people also look at, or is it something?
I don't think it's been looked at before, but I'm not that well versed in all the dynamical systems literature, so I'm not going to give you a definite answer that it hasn't been looked at. I don't think so. Where was I? Oh yeah. So it's not so hard to see that the usual definition of property T is equivalent to this one. We'll say that a group has Kazhdan's property T if it's generated by a finite generating set S with the following property. For every epsilon, there is a delta, so that if a vector is almost fixed by some unitary representation on the set S and up to an error tolerance of delta, then there exists a vector that is actually fixed and which is close to the almost fixed one. If this condition and this psi is actually fixed by the representation. I guess you all know
That's
examples.
psi 0 below, right?
Hmm?
That's psi 0 there, it's the last display.
Yes. Sorry about that. Yeah. It should be psi 0. It's not the same as that.
Is it for some unitary representation or for every?
So it's, yeah, I guess I phrased it a little unfortunately. But, it's for every, yeah, it has to go for every unitary representation. It has an almost numeric vector. Did I make any more mistakes on the slide? So I guess I don't know examples of groups with property T, but there was some room left on the slide. SLNZ when n is at least 3, but not SL2Z. And then we have co-compact lattices in SPn, 1. Interesting because it gives examples of groups that are hyperbolic and have property T. That won't enter into the rest of the talk. Okay. So based on that, we're going to prove this lemma, which will immediately imply the theorem. So if you have a group property T in this generating set S, then for every epsilon there exists a delta, so that if two actions are close together, in this sense, on S, they're close together, then there's an automorphism that conjugates them. And you can rig it so that the automorphism is close to the identity automorphism. I hope it's clear how that implies the theorem. We won't exactly get this, right? We'll get an action and then a conjugate on the other action. They'll be close together. So, how do we prove this? So, it's a general philosophy, I guess, in this ergodic theory / Feldman algebra theory, of that if you have an action on an abelian Feldman algebra, then there's a way of constructing a bigger Feldman algebra that encodes the action, in the sense that there are unitary operators, such that the adjoint action by such a unitary implements the action. Okay. So for example, the cross product from Neumann algebra theory is such an M. But we won't quite be dealing with the cross product here. A version of the Feldman-Moore construction. You know what that is. is just an overview. I'll go over these things in some more detail. So you construct this M, which in some sense encodes the action. And to study that inclusion that you get of A and M, you build the basic construction of Vaughan Jones. So it's become fairly standard over the last few decades. That if you want to study an inclusion, you study the basic construction. And it's a new phenomenon algebra that's generated by this M that you constructed, as well as a projection from M onto A. I guess you're sort of reflecting A about M. And this basic construction comes equipped with a trace, which is not a state. It's not defined everywhere. But it still gives rise to an inner product with this formula. And by completing with respect to this inner product, we get a Hilbert space. And that's the one on which our unitary representations act. And yeah, define an appropriate unitary representation. It's not obvious how to do that, but it can be done. And you do it in such a way that this distinguished vector here is almost fixed. EA. So then, by property T, there's a vector that's close to EA, which is actually fixed. By some trickery, you can make it so that this vector, which is just somewhere in H is sort of an abstract thing. Right? We can make it so that it's actually inside the basic construction, inside the Neumann algebra. So we can use functional calculus to replace it by a projection. So we get a projection that's fixed by the representation, and that is still close to this EA gadget. And then the last step is to show that E is of this form, VEA, V star, where V is in the normalizer of A inside M. It's an element of this group. Elements like this are in the basic construction. It is generated by EA and elements of M. And then the fact that E is fixed by I is going to tell us that this automorphism here, which acts by just conjugating by V star, is the automorphism that we want. We'll conjugate the two actions and be close to the identity. Okay. Any questions at this point? I mean, I'll go over this in more detail.
Totally mysterious. It's totally mysterious
Yeah.
to us.
Yeah, I guess it is. It's not as mysterious to me. But yeah.
So property T is used as the first step to go from
It's used here.
almost fixed to fixed vector.
Yes.
So could you say probably what is this basic construction of Vaughan Jones in some example? Or is blue reaction or whatever?
It's a bit tricky, actually. And there are examples, but they're not. I don't know if they would help you get an understanding of this situation here with the actions.
Or some tell us some property, usual property we use of this. I don't know. Some fantastic property it has.
I mean, it has a lot of, I mean, it's named after Vaughan Jones for a reason. Right?
Yeah, we all like Vaughan Jones, this is for sure. But I'd like to understand this object we see for the first time. It's basic for you, but not for us.
Right. I mean, Vaughan Jones used it. If you just think anything I would say would just make it more confusing rather than less confusing, to be honest. Vaughan Jones used it to prove his index rigidity theorem. That there's a von Neumann, you have a Hilbert space with a von Neumann algebra acting on it, and there's a dimension you can look at. And maybe I'll leave that to the questions. Yeah.
Okay.
Take us a little far afield.
Isn't it just a tensor product with A with the bounded operator on L2 gamma in this case? It's the conjutant
not quite.
of A inside L2 of the original space tensor L2 gamma. So yeah.
Sorry, if A were some sort of fixed point algebra of some action on M, then the basic construction would be a cross product.
Well, but in this case, I mean, A is just the L infinity with some space, right? In this case, it's, I mean, really talking of the Abelian algebra inside the cross product, and in this case, it's just tensor product with a type of factor.
Right, yeah, that's true. But I don't know if that helps, geometric group theory stuff.
So say again, so it's
So it's
a
just
product
a-
of L infinity or with what?
With the bounded operators on the L2 gamma.
Okay. Mm-hmm. Yeah, it helps.
Now we're going to construct this M thing. But let's take a step back and assume that M is already constructed for us. So we have a von Neumann algebra with a faithful normal tracer state on it, which means that we have this condition here. Of course, it's automatic when you have an abelian von Neumann algebra. So of course, M is born acting on some Hilbert space. But we can construct a new Hilbert space where M acts in an especially nice way. So we have this trace, so as before we can define a norm. In fact, this norm arises from an inner product coming from the trace. So that we have M an inner product, so we can make the Hilbert space completion. And then we can let M act on L2M just by left multiplication. For each element x of M, we get this operator Lx, which takes y to xy. And that extends to an operator on all of L2 of M. L2 of M contains M in the subspace. This is called standard representation. And of course, this left multiplication representation has a partner. The right multiplication representation. And they're related by this formula. Where J is the extension of the involution. Right? We can take adjoints of operators. That extends to an antilinear unitary operator. Now we have this, we started with this A, and we want to construct this M. We'll get an especially nice inclusion. We call it Kazhdan inclusion. So that means that A is a maximal abelian star subalgebra. So it's abelian, it's any larger subalgebra is not abelian. And M has to be generated by the normalizer of A and M. Again, this once we have such an inclusion, well, they sort of, an inclusion like that sort of encodes an orbit equivalence relation. That won't really come into play in this proof. You can always encode an equivalence relation into such an inclusion, which is important when you're dealing with orbit equivalence. Anyway, we have this A inside M, so we can close A in the 2 norm to get a subspace, closed subspace of L to M, and then there's an orthogonal projection, L to M onto L to A. And this won't really come up very much, but it extends to an especially nice map from M into A, and not just L to A, which has some nice properties, so conditional expectation. So it would come up in computations if I showed you all the computations. Anyway, so we have this projection acting on L to M, and we have M acting on L to M. So we can look at the Feldman algebra that they generate. That's the basic construction. It is sort of an amplification of A. That's one way of looking at it. Way of blowing up A. Anyway, we get this Feldman algebra. Inside, there's a special subalgebra, which is generated by left multiplication by elements of A and right multiplication by elements of A. Okay, so that's an abelian subalgebra, which we'll call script A. So now with all this set up, there are some maps we want to look at. So these won't be defined on all of script M, but they'll at least be defined on the span of elements of this form. I'll tell you how they act on elements like that. That will give you some idea of how these maps work. So we have a trace, which again is not defined everywhere, but on elements of this form, it's defined like that. And there's sort of a conditional expectation of script M onto M, which is the one where if you take this and compose it with the trace on M, you get the trace on script M. And then there's a center trace. So a trace that has values in the center of script M, which turns out to be this algebra of right multiplication by elements of A. And it works like that. So I didn't give these maps names because we're only going to care about the restrictions to script A. Okay, so we have these densely defined maps from script A into A and into JAJ. So sort of from script A onto its 2 generating legs. And the point is that we have this lemma. If you have a projection in script A that's mapped to 1 by these sort of projection maps, then it has to be of this form. So it's a technical tool for constructing this B. Okay. So that's all we need about the basic construction. And then finally, before the proof, I wanted to talk about this Feldman-Moore type construction, the way of coming up with M in the first place. So the Feldman-Moore construction originally is where you have an equivalence relation on some probability space, and then you have L infinity, and you build a bigger Feldman algebra that contains L encodes the equivalence relation. But you can formulate all of this without any measure theory. And to do that, you need the notion of a full group on some Neumann algebra with state. And basically, a full group is a group of automorphisms which is closed under patching. So if you have a bunch of automorphisms in G and you restrict them in such a way that so A is sort of, it's L infinity of X. So we can take X and split it up into pieces. So these are sets. But, they're characteristic functions or projections. So let's say that this is the cut down of A by P1. So if this is L infinity, this is just all the functions on the set corresponding to P1. We assume we can cut up the image as well into things like this. So we have thetas in G there. So we can look at the piece coming from that projection. We're assuming that these parts that are disjoint from each other. Just the same as saying these projections, they multiply to 0. Right? And then we can, of course, look at the automorphism, which is theta 1 here, theta 2 here, and so on. And by gluing these all together, we want to get a new automorphism in G. So that's what the full is. Rephrase like that. We have this partition of unity in A, and then we have these automorphisms that also add up to 1 when you apply them to the PS. And then you define this global automorphism like that, which is the one you get by gluing all these together. If all the theta ends are in G. That's sort of the same as an equivalence relation.
So go back a second. That's your choice of partition each element of G. You have this choice of PNs. So you're saying for every
choice
element
of PNs.
theta there exists these PNs and these theta ends.
I'm saying for every choice of PNs and theta ends that satisfy this property. If the theta ends were in G, then this patched automorphism is also in G.
Okay, thanks.
Okay, so yeah, given a full group, you can construct this from Neumann algebra M, which is going to be generated by A, and unitary elements indexed by elements of the full group, such that M has a faithful normal trace on it, which we needed for all this machinery to work. It's defined like that. Moreover, A and M is a Cartanian illusion, and these unitaries implement the action in this way. So just from this data of full group and this full Neumann algebra, the data of Neumann algebra A to get this M. And you can construct it like this. So you start with a star algebra of finite formal sums, like this. The coefficients A theta in A, and these indeterminates U theta, and then you define the product, and the involution in such a way that this holds. You can do that. And then you define a linear functional on it, by this formula. And then the point now is that this tau tilde gives us an inner product, or a pre-inner product. That requires a little work to show, right? We have to show that the inner product of x with itself is non-negative for every x. That's something one can do. And then you let M0 act on itself by left multiplication, and that extends to an action on this Hilbert space completion, coming from this inner product. And then you close M0 to get out. So the tricky thing is showing that A is actually a maximal abelian subalgebra then. Otherwise, it's pretty straightforward.
So how is it related with a cross product
Oh yeah.
of A with the full group?
So if you have just a regular group action, then you can look at the full group generated by the image.
Right?
And if the action is free,
Yes.
then the thing you get from this full group is just a cross product. If the action is not free, then you get something else. Because if you just took a cross product, then A would not be a maximal abelian. But in this construction, A is always maximal abelian, no matter if the action is free or not. And that was that. All right, so now we can draw the lemma. Try rephrasing here. So we start with these two actions. Well, we start with epsilon, we have to pick delta, and then given these two actions, we have to find this theta. So that epsilon's a given. And then, it's not true that the exact same delta as in our definition of OGT works, but almost. You have to divide it by 10. So then we have this full group generated now by the images of both of these actions. And then, remind you of the notation. So this gives rise to the Feldman-Moore construction M. These canonical unitary operators and this trace, which I called tau twiddle before. It's just tau because it extends this tau. Do the basic construction, and then we have this script A inside script M with these two projections onto its legs. A and J. J is just right multiplication by elements of A. A is left multiplication by elements of A. L2M. We want to construct a unitary representation and find an appropriate projection, and then show that it's mapped to 1. So, as before, the Hilbert space will be the completion of M with respect to the inner product arising from the trace. And then the unitary representation will be defined like this. So I know this doesn't really tell you very much. So yeah, this is how it acts on these X, E, A, Y things that form a span of dense star algebra. The basic construction. And this turns out to actually give you a unitary representation.
I see. So the action involves both initial actions, sigma and rho.
Yeah. And we're sort of making them independent of each other by letting, we have U here, that's just left multiplication by U. And then we have J, U, rho of G, J, which is right multiplication.
So these two actions, this sigma and rho conjugated by U, do they commute?
Say that again.
These two actions, sigma on one hand and rho conjugated by J, do they commute? We're used to thinking of a left action of a group on itself and the right action of the group on itself, you commute. That's very familiar.
Yeah, I mean, these two components here commute with each other. That's what you're asking.
Right.
This exact formula will, will come up again when we actually show that the V that we produce does what we want. So first off, we have this little computation. So pi s of EA minus EA turns out to equal this distance here. Where this 2 norm comes from the trace on M. And this notion of distance here is equivalent to this notion of distance. So there's up to some constant, these are the same. Didn't want to complicate matters too much. So, so this EA is almost fixed because the two actions are close together. Okay, so then by property T, there's a vector in H which is close to EA, and which, I did it right this time, and which is actually fixed by the group action. By an averaging argument, you can replace this Hilbert space vector psi by an element of script A. And the reason for that is basically that EA belongs to script A. So we can do an averaging argument where we let, act on it by pi g, take the convex hull. Anyway, we end up with an element of script A, which we can use instead of psi. And then we look at the spectral projection. By appropriate estimates, we get that E is still close to EA. I guess I'm lying a little bit here. But it's 3 yet. And E is still fixed. Basically because the fixed point algebra of the representation is a von Neumann algebra. Von Neumann algebras are closed under the Borel functional calculus. So now we want to show that this E thingy is of the form E, EA, E star, right? So we take these two projection maps, apply them to E. And then now, since it's easy to show that these maps commute with the representation, and since the actions are ergodic, these two things will be scalars. And you can write down formulas for these that show that since E is a projection, these are sums of projections. Right, so basically these are integer valued functions, and we're showing that they're constant. Okay, so they're both equal to some integer multiple of the identity. And then the fact that E is close to EA shows that this constant has to be strictly less than 2, so it automatically has to be 1. So then E is of the form we want. The fact that E was fixed by this representation, and the way in which we defined it, shows that we have this identity here. VEA, V star is equal to this unitary times EA times the conjugate. Yeah, joint unitary. So this shows that, so by multiplying by V star on the left and by V on the right, we get that this unitary operator here, which is an element of M, commutes with EA. It's not too hard to see that if you're in M and you commute with EA, then you're actually in A. That means that if you take the adjoint action of this on A, it's just the identity. It's unitary in A, so it commutes with everything in A. So, and the adjoint action of this is just what you get from this if you move rho G to the other side. we end up with this, which is what we wanted. And this automorphism is close to the identity because B is close to 1. Series of identities.
So it seems to you to be of great importance to you that A be maximal abelian in M, right? So where how does this enter in the argument? And which step?
So it enters in. So when I said that these are sums of projections,
Yes.
it enters in there because when A is a Cartan of algebra of M, there's a special kind of decomposition of elements of script A. And that's what I'm using to show that these are sums of projections. At least there it comes up.
Yeah, because A itself is not very, it's not unique. But there are maximal abelian doesn't mean that it's uniquely defined. Well, it's not invariant under automorphisms of M, for instance.
No.
No, right?
Here we're starting with A.
Yeah.
The important thing is the relationship between A and this new thing that we're constructing. It's not. I'm not sure how to answer your.
So, you see, okay.
And there are results where it's important that A is the just unique A. But that comes down to proving orbit equivalence, because the orbit equivalence relation is encoded by this sort of inclusion. So that's important when you have like rigidity results. You prove that if two von Neumann algebras are isomorphic, two von Neumann algebras coming from an action are isomorphic, and the actions have to be orbit equivalent. But it's quite different from this.
Yeah, it's not the same story.
This gadget here, this Feldman-Moore construction, is important in a lot of contexts. The main point here is that it exists. Start with A, build this down. These unitaries that behave the way we want. Right. That was the proof. So I wanted to end with some open problems.
Yes.
On a lighter note. So the proposition and the theorem that I mentioned both raise the question of if every group without Kazhdan's property T has many free ergodic actions that are non-conjugate but that are still approximately conjugate. If you could show that every group without property T has two such actions, then we would get a characterization of property T. That's one open question. And there's a related question.
There is a related fact in ergodic theory, which is true. If you replace approximately conjugate by orbit equivalent, then the corresponding statement is true. Seems to be something of that sort is true. No.
And there's a result that says that every non-amenable group has uncountably many non-orbit equivalent actions. That's slightly different. I don't know if it's known that you can always find a lot of non-conjugate actions that are all orbit equivalent. related question is which groups have many non-app conjugate actions? Those are the ones you're asking. So we were able to prove using work of Gregory York and Conwise that every non-amenable group admits at least two free ergodic non-app conjugate actions. Right, so for groups without property T, this comes down to the fact that there exists a non-strongly ergodic and a strongly ergodic action. And that's what Conwise proved. Also, every group with Kazhdan's property T admits uncountably many non-app conjugate actions because they have uncountably many non-orbit equivalent actions. So they're non-conjugate, so they're non-app conjugate. And also, based on the work of Kekris and Albert Elek on this weaker notion of conjugacy that I didn't really talk about, it's also known that every free group admits uncountably many mutually non-app conjugate free ergodic actions. So the second open question is, does every non-amenable group admit uncountably many mutually non-app conjugate free ergodic actions? These are probably both difficult to answer. Okay.
What I could catch from your talk is a trick that allows to make the difference of two actions. Right? You have two actions, rho and sigma, are some probability space. You can make a difference of them. So of course it does not exist as an action on a probability space. So it exists as an action gamma on the Hilbert space associated to this basic construction made from this cross product. You need all this elaborate construction to produce the difference between two actions. So if the two actions are sufficiently close, then the difference has almost infinite terms. Yeah, right. So that's something we should remember. That's crazy. This linear operation of taking the difference of two objects. Of course, we cannot be made in our usual world, but it can be made in your world.
Yeah.
Right? Good to know. The people in now is online.